we begin our afternoon session. Thank you for coming. It is my pleasure to let you know that we have another world expert, an English physicist and particle physicist, Professor Amanda Cooper-Sarkar from the University of Oxford. Professor Amanda Cooper-Sarkar is an expert on deep inelastic scattering and Parton distribution functions. Amanda Cooper-Sarkar received his PhD in particle physics from the University of Oxford. After working as an exchange fellow at the Tata Institute of Fundamental Research in Mumbai, in India, and then at the National Laboratory for High Energy Physics in Tsukuba, Japan, she returned to England as a research associate at the Rutherford Appleton Laboratory in Oxfordshire. Her gold line passed through CERN at Geneva, and also as senior scientist at Rutherford, and so on and so on. And finally, she became a professor of particle physics at the University of Oxford. Professor Cooper-Sarkar was a part of ZEU's S collaboration and also part of the Atlas collaboration in CERN. She's a winner of a number of prizes, amongst them the Nuclear and Particle Physics Divisional Prize of the Institute of Physics and the famous James Chadwick Medal and Prize for her study in deep inelastic scattering of leptons on nuclei, which has revealed an internal structure of particles. It is pleasure and honor for us, for all of us, that she has agreed to give a series of lectures at this school. Please join me to welcome her very warmly. And invite her to begin the lecture. Thank you for coming.
Okay, well, these lectures are going to be a bit different than what we've had for the last day or two, because I'm not concerned with the cosmos and the early universe, but with right now today at the Large Hadron Collider in Geneva, right? As I was introduced, it is my expertise is on the Parton distributions. Now, what we all wished, I think, when the collider was being switched on was that this wouldn't really matter very much, because a great big resonant peak for some new physics would just show up out of the background and exactly how it was formed wouldn't matter, right? But that hasn't happened. And it really does matter how well you know all the cross sections, both standard model and beyond standard model. If you're trying to look for new physics, you'd better know what the old physics is, what it is you think you already know, and you'd better know it at really some quite high precision now. We thought we were going to be able to get away with a sort of so-so precision and the new physics would be obvious, but it isn't. So we really need to know what's going on. And here's the point. So our problem is, of course, that we couldn't build an E plus E minus collider with high enough energies to really access the Higgs and other new particles. The Bremsstrahlung radiation is too much, so we have to build a proton-proton collider. And the thing about protons is, of course, that it's not the protons themselves that are really doing the colliding. What's doing the collidings is the partons within the proton. So what's happening when you're colliding one proton with another is that it's actually some sub-particle of the proton in each side, which is making the hard sub-process. And if you want to calculate the cross-section for producing something new, which I've just called X here, that could be the Higgs boson, or it could be well-known things like the W and the Z. It could be high ET jets, in which perhaps you're hoping to see evidence of new physics and so on. Whatever you're doing for the cross-section you observe, you're going to have to convolute your calculation of this hard sub-process with the Parton distribution functions on each side before you get what is actually measurable. So you really have to know what this stuff is. Now, this is a diagram of the kinematic region being probed at the LHC. Right? So the kinematic region at 13 TeV is shown here. And the variables on the plot are the scale of the process. What that would be in this case is the invariant mass squared of this sub-process, right? So how deeply you're probing. Are you probing up to scales of 10 TeV or so, hoping to look for new physics? Or are you calibrating your machine looking for well-known physics like the W and Z boson? Or indeed the Higgs, which we found, 7 years ago? Almost to the day, actually, isn't it? Yeah, almost to the day, which would be in this region at 125. And this other axis, what does it mean? It's broadly called X. What it refers to is the subfraction of the proton's momentum that is being taken by these partons on either side. But the collider is a little complicated because in each interaction, two of them enter. So, and here I've only got one variable, so that's why you see these lines coming on the picture to tell you what's going on, and I'll try and sketch what this means. That's okay. So, okay. Here's one of our detectors with beams coming in at either side. Now, as I said, what's actually happening here is it's not the proton beams themselves, it's the partons within them that are doing the interacting. Suppose each, just for coincidence, for illustration's sake, they each had exactly the same fractional momentum of the proton on either side. Suppose that was the case. Then they would actually collide dead center in the middle, right? And that, as experimentalists, we call that rapidity of zero, the center of the detector. Right? But of course, most of the time, one of them will be carrying a little more than the other, and they'll, collide somewhat off-center. And that means that the particles you see are going to be splaying out at various rapidities. Now, the central detectors go to rapidity 2 and -2, and then we have other further detectors around the outside. I won't try and sketch all of it, but we can get out to Y4 and Y-4 with our additional detectors. When the Y is not zero, it means that the subfractional momentum of each of the partons was different, and that's actually shown up on the top of this thing here, right? The X values are the invariant mass of your process, M sub X, divided by the overall center of mass 13 TeV, exponent plus or minus y. So according to the value of y, it tells you we've got one parton with a large amount of the proton's momentum and the other with somewhat less, or vice versa, because these are identical particles. It's a proton-proton identical particle system, so you can't actually tell the difference in the end between y of +2 and -2, right? It's the same. Now you look here, these are the y lines. So the center of the detector is here at y of 0. So say if you're producing something like a Higgs, something around 100 GeV, the two partons have a subfractional momentum of around about 10 to the -2, just a bit less, right? But if you're going off-center, then one of them will be having a bit more than that, and the other one will be having a bit less, and so on, according to, exactly where it scatters in the detector. Now, this would be a complicated way of actually trying to find out information about the parton distributions. We'd better already know them and simply apply them in this collider, right? So where do we get to know them from? We get to know them from what are called the deep inelastic scattering experiments, of which have been run for many years, but the largest kinematic range covered by any of them is that of the HERA collider, which was an electron-proton collider in Daisy, Hamburg. It ran from 1992 to 2007. So, I'll do that. As an overview of what I'm going to try and talk about, right, I'm actually going to try and outline how we came to know what we do know about the partons inside the proton and how it fits in with QCD. Well, first of all, with the simple quark parton model, and then with QCD as an improved parton model, and how you actually calculate. You see, we measure them here. How do we know what they are there? We can only know that because QCD itself predicts the evolution in scale of these parton distributions exactly. The problem is that QCD itself does not predict what the parton distributions themselves are. Now, what does it mean, parton distribution function? It means how the partons are distributing themselves in the fractional momentum of the proton, right? This is actually not calculable because it's a non-perturbative problem. I mean, maybe it is in principle. Indeed, people using, lattice gauge theory, right? This is one of the problems they try to solve. But they're rather far at the moment from really being able to calculate for you a parton distribution function. This is why we have to measure them. We then go on and say, well, how is it from the measurements? How do we get these? What are the assumptions that go into it? And we'll also go a little bit beyond the standard theory for getting at this, but that will come. There are many references for this. This happens to be one of my own favorite references for it, but there are many standard textbooks in which these things are described. Okay, so to measure parton distribution functions, what you really need is deep inelastic scattering. So as I said, that is in general, a lepton-nucleon interaction. So what we're trying to do is find out about something big like the nucleon by firing in on it something small, like a lepton, an electron, a muon, a neutrino even will do for this, right? In essence, it's not unlike what Rutherford first did in finding the nucleus. He was trying to fire into a big, into a nucleus, a small particle, and he found that there were into the atom. He found there was a nuclear center. We're doing the same thing with protons, firing things in and seeing if there is any structure in there. And there is. Only the surprise is that if at least, at undergraduate level you've learnt about the simple quark model, you're usually taught that the bookkeeping of hadrons, baryons, and so on in terms of quarks is with the idea that there are 3 quarks in a proton, right? 2 up and a down. This is a lie, right? Or rather, it's an oversimplification, right? There are 2 U's and a D, what you would now call, borrowing a term from chemistry, as valence quarks, which give it its overall flavor properties. But there's a whole lot more stuff in there as well. There's a complete sea of quark-antiquark pairs, and there are gluons, and they're already there. Even at a proton at low scale, they're already there. It's not that you start with just the 3 and the evolution creates more as they quarks radiate gluons and so on. As far as we can tell, down to the lowest scales we have protons, the QQ-bar-C and the gluons are already there. Now, what I put on this page is deep inelastic scattering as seen by a theoretician here, and as seen by an experimentalist here, right? So what are we using to describe it theoretically? There's a lepton coming in, incoming 4 vector k, outgoing 4 vector k prime, lepton in, lepton out. It's exchanging a vector boson. Mostly I'll talk in terms of photon exchange, but W and Z exchange is allowed in this process as well if you're at high enough energy. And it hits a proton, and that breaks up into a final state. And the kinematic quantities you need just to follow what I'm talking about are the four momentum exchange between incoming and outgoing, k minus k prime is q, and its square, which in fact is negative. This is a space-like process. So its e squared minus p squared c squared invariant is negative, right? This is a virtual particle. It can never be on its mass shell because it's got a negative q squared. So we often talk in terms of the negative of that negative quantity in order to have a positive quantity big q squared. There's the center of mass energy of this whole thing, k plus p squared. And there are various four-vector invariants you can construct out of the four vectors on this plot. At the moment, on this page, all these are a four-vector invariants, but we will learn what they correspond to physically in a little while. Now, if I'm an experimentalist, instead of that, what I see is a proton beam coming one way, an electron beam coming the other way. There's the scattered electron going off, and here is all the stuff there, the rest of it, the breakup of the proton. You can actually more or less measure that in its direction as well by putting together all these jets of particles. But what I want to emphasize here is that these invariants here, right, are just functions of the four vectors, and we can calculate what they are in terms of the incoming electron energy, incoming proton energy, that gives us our center of mass energy. The q squared, that's the exchange momentum squared, is given in terms of incoming electron energy, outgoing electron energy, and the angle between the outgoing electron and the beamline, which, say, on the real detector looks like this. And then these other four-vector invariants are also given in terms of these kinematic quantities. So they're all completely measurable, right? You do these experiments, you measure these quantities, and you know all there is to know about the sub-process. Well, almost. Now, schematically, right, what's going on here, I think, just flipping back there, you can see the way we're going to calculate this diagram is in terms of the convolution of a lepton tensor for this vertex and a hadron tensor for that vertex. We know all there is to know about the leptonic tensor. That's well-known electroweak theory. We don't, in fact, know all that there is to know about the hadronic tensor, precisely because we don't actually know. We're not scattering. Wouldn't it be nice if we could just scatter off bare quarks and gluons? Then we could calculate that in QCD. But we can't do that because they're confined in protons. And as I've just said, we don't really know enough about how they're confined in protons. So we don't know everything there is to know about the hadronic tensor, but we do know that it must be constrained by Lorentz invariance, so it can only have certain kinematic properties. So if I'm talking here about a charged lepton scattering through a neutral current, that's the photon or the Z, but let's make it the photon for simplicity at first. The cross-section for this, right, in terms of the variables x and q squared that I already introduced, is given like this. And in fact, this is the easy bit. This is the electroweak bit. You've got your propagator for the photon 1 over q squared there. That's the 1 over the q to the fourth. You've got your fine structure constant squared there. That's just the simple charge at the electroweak vertex. And then all the rest of this is to do with the hadronic tensor, which, as I said, we don't know what these functions of x and q squared are, but we know that they have to take certain dependencies on the kinematic invariant y, which is related to the scattering angle. So we know the general form of it, although we don't know exactly what's inside these functions. These functions are called structure functions. And we will find out that they are related to the parton distributions inside the proton as we go along. Just to illustrate how this works again, if I'd used instead a charged current exchange instead of a neutral current, a W, the difference would have been that I'd have needed here a W propagator, and I'd have needed a weak charge in terms of the Fermi G constant. Otherwise, it has a very similar structure. So the point is that when you measure the cross-section for this, you're measuring, it's not quite the same diagram as this, but you're measuring let me take it back to here. You're measuring angles all over the kinematic plane. You're measuring both x and q squared fully, right? And so you can actually measure in slices of different values of x and q squared what are the cross sections. So in principle, you may not know what these structure functions are, but you can measure them by binning your data in y for the angle, in x and q squared for the cross section, and finding out what are these values in each bin of x and q squared you've got. In principle, it's possible. In practice, it's actually very difficult to have enough data and accurate enough data to do that, to do that well, until, I might add, until we did have the HERA collider, and then you can do it pretty well. We'll see how that goes. So, these structure functions are parameterizing our ignorance of the hadron sector, but they are measurable functions of x and q squared. We might not be able to calculate them, but we can measure them. Now, so far I've made no assumption as to what goes on when the vector boson probe hits the proton. Right? Now let's start making some assumptions, and we will be guided in making the assumption by Feynman, right? Because this was his idea, right? He said basically, what if, when this scattering happens, what's really happening is that a single quark coming out of the proton that had momentum p, a single quark taking a subfractional momentum xp, is actually what's being hit here, right? That is what's actually happening. A single quark is being scattered, the rest of them are kind of spectators to the interaction. After this has happened, because color is confined, a great deal of mess happens in terms of color recombinations before you get out again. But that was not his business. He's talking about the original interaction. Now, if you just look at the four vectors here, his assumption was quarks are massless, right? Close to being true. So this outgoing quark has a four momentum, xp, for the incoming quark, plus q for the vector boson that's joining it. And it's going to be massless, so when I square it, I'm going to get 0 for its mass, right? Now square that out, right? xp plus q squared all squared, we square it out. The total is about 0. However, what is p squared? P squared is just the mass. Right? It's the e squared minus p squared c squared 4 vector for the proton, so it's just the mass of the proton. And the mass of the proton is not very big, right? It's sub GeV. So his next assumption was to say, well, I'll also assume that p squared is 0. Right? We're going to work at high energies here. These are small things. So what am I left with? I'm left with little q squared plus 2xp dot q is 0. So if I turn that equation around for x, given that q squared was negative, as I emphasized, it tells us that x is q squared over 2p dot q. Now what's remarkable about that is that x was, a couple of pages ago, I just said that's a simple combination of 4 vector invariants, we can measure it. What I'm doing now is saying, well actually, that particular invariant also happens to correspond to the fractional momentum of the struck quark in Feynman's picture. Right? So not only can we measure x, but what we realize what we're measuring when we measure x is the fractional momentum of the struck quark. Okay, so this is just a page for some notation which will be useful to us later. Right? I don't know to what extent you all would have studied scattering theory, if at all. Well, what scattering theory tells us is that the total cross-section for any process, in this case the vector boson-proton subprocess, the total cross-section for it is given in terms of the imaginary part of the forward scattering amplitude. Right? That's a theorem in scattering theory, we will just accept it. So if we want to calculate the total cross-section, we can instead calculate this elastic process, which can be easier. Now, when we look at the elastic process, what we're doing is saying, using Feynman's picture, we think the way this elastic process went is that the incoming vector boson hit this quark, it became a quark with a slightly different form momentum for a while, and then if it's going to go back elastic, it'll go this way, right? This diagram is called the handbag diagram, and it dominates the things we're talking about, right? Why is it called the handbag diagram? Here is a handy visual aid as to why it is called the handbag diagram, right? But the thing is that it's a diagram we've used lots, but it's not the only game in town, right? And I will show you other diagrams that could be important as we go on. So, let's calculate something that hopefully, is familiar if you've done just a little QED, right? You would know how to calculate electron-muon scattering, right? So you have an electron current in terms of your Dirac spinners and your gamma functions, and you have a muon spinner, and you put them together in terms of electron current, muon current, and the propagator, as here, and you then average over all the initial and final, so sum and average over the initial and final spins, and you come out with the cross-section for the process, which looks like this. This is something which hopefully you could do yourself if you've studied enough Dirac mathematics, right? Now, there was one thing I did here, just deliberately. I wrote the muon and the electron charges different from each other, one as E and one as E prime. And that comes through as E squared E prime squared here. And if I put the answer in terms of the fine structure constant, I'll have the ratio of E prime to E in my final answer. That's going to be useful because we'll now generalize it to quarks, and quarks do not have the same charge as the electron. They have 2/3 or minus 1/3, and that's the ratio that's going to come in there. Now, the result for this scattering process comes with two terms in it, one which will be isotropic in angle, and one which is non-isotropic, and they come from the way that the electrons and the muons line up their spins, right? If they line up their spins against each other, so if they're either both left-handed, which is what I've illustrated, or both right-handed, then the overall spin down the axis will be 0, and you can have an outgoing isotropic distribution. If instead one is left and one is right-handed, they line themselves up along the direction of scattering, and the one thing you can't do is rotate that fully by 180 degrees. There is no projection operator for going from this way completely the other way, but there is a projection operator for angles in between, and that's just incorporated in this 1 minus y squared. What it's saying is this will be 0 when y is 1, which is the same as the angle theta, the scattering angle, going to pi. So it's easy enough to understand qualitatively the kind of terms that come into this. Now, to generalize this to scattering electrons from any fermion with a different charge, as I said, if say it's a quark I'm thinking of, what I have to do is write the E prime over E as some general charge. So E sub I will now stand for either 2/3 or minus 1/3, depending on the quark I'm scattering off. And the other modification is the quark that you're scattering from will, of course, not have the entirety of the proton's momentum. It has subfraction x of it. So instead of writing the center of mass energy S, I'll write XS. But otherwise, my formula is the same, right? That's for one quark inside a proton with a subfraction momentum x. Now what about the whole thing, all of them? I'm going to have to sum this up for all quarks or antiquarks with their varying fractional charges. And that will then give me the scattering cross-section for an electron from a hadron, right? So I'm summing up all these separate scatterings from quarks incoherently. And the meaning of the quantity q sub x then in this formalism is, this is the probability of the quark having the subfraction x, right? So if it's got subfraction x, it's this. And you have to sum over all of those possibilities times the probability that the quark actually did have that subfractional momentum, right? Now let's compare that scattering cross-section to the general formulae we had. There's the formula I've just written. and there's the general one. Right? Compare one to the other to find out what is Feynman's prediction for what are the structure functions. And when you look at that, it's extraordinary. This structure in Y that multiplies the F2 structure function is exactly this form. And so what he predicts, this is the quark-parton model predictions of Feynman now, is that the F2 structure function, something we can measure, simply relates to the weighted probabilities of there being quarks and antiquarks with a certain subfraction x. Because it's overall multiplied by x, it's not actually the probability for there just being a quark, it's its momentum distribution, a quark with momentum x, weighted by its charge squared. And note, the general expression had q squared in it. The quark-parton model doesn't. In other words, what Feynman is predicting here is that the thing scales. It does not depend on the scale q squared. Right? This is Bjorken scaling, and it's an extraordinary result, because if you think in terms of things like, form factors for protons, they're very strongly dependent on q squared. It certainly wasn't expected that this would be the case when you were doing deep inelastic scattering of protons, that you would get it independent of the scale. But the other extraordinary things are that the other two structure functions would appear to be exactly zero. We don't need them in the quark-parton model. Why don't we need them? Well, we don't need the FL because we were working with spin-half quarks. When we did this likening the scattering of the quark to the scattering of the muon, you were carrying over the fact that the muon is a spin-half fermion, saying therefore also is the quark a spin-half fermion. And it's because of that assumption that you get no longitudinal structure function. The fact that you don't get this other structure function, xf3, that has a different structure in angle, is because we were considering only photon exchange. But so far so good. The question here is, when I constructed this model, right, I just put in both quarks and antiquarks. This probably seems completely natural today, but it wasn't that natural at the time, because at the time people were still thinking in terms of 3 quarks in a proton. So why would you put antiquarks into the sum, right? Well, there's a reason for it, but before we get there, let's look at the experimental evidence that these things that we've said here are true. So the two things we're going to look at are, is it true that this quantity scales, and is it true that the longitudinal structure function is 0? This is the quality of the data when this field began, which was around 1970 or so. Right? There's the F2 structure function plotted against q squared for a certain value of x. It is indeed pretty flat. Right? That's the observation that really got Feynman excited at the time, right? That it looks flat. And here is a measurement of the ratio of the longitudinal structure function to the transverse. It should be around 0 if the longitudinal structure function is 0, and it is, right? This is what established the spin-half nature of the partons. So this is how we, right from the beginning, began to establish that we knew what was going on inside a proton. We've got spin-half partons in there. Now, another thing you can use to scatter is the neutrino. It's kind of neat to use neutrinos because they're handed. So if in fact you're using a neutrino to scatter from a fermion, right, then they both like to be left-handed, right? Because they both like to be left-handed, this neutrino fermion scatter will be independent of angle. Similarly, if it was antineutrino with antifermion, right, both right-handed. If instead you scatter your neutrino from an antifermion, one is left and the other is right, that gives us net spin down the beam direction, and this is not isotropic. So that's just breaking down the two possibilities we had before for an electron, saying that neutrinos select what they want. And clearly, the same is true if it was antineutrino fermion. So, This was done in a regime when we didn't need to worry about the propagators. It was at lowish q squared and the propagator term was 1. That's why I'm writing such a simple form for the cross-section, the isotropic and the non-isotropic bit. So when you scatter with a neutrino from a quark, you just get an isotropic term. From an anti-quark, you get a 1 minus y squared term. Do the same thing with antineutrinos and their roles are reversed. So in fact, in the 80s, there were lots of experiments being done at CERN on neutrino and antineutrino scattering, looking at the differential cross-sections in terms of the angle and seeing what happened. And we have here, right, this is the distribution for neutrinos against the variable y, which is just a measure of the scattering angle, and this is that for the antineutrinos. Now, look back for a minute. If we had no antiquarks, this would be purely flat, and that would be purely 1 minus y squared. What do we see? This is not quite flat, close but not quite, and this is not quite purely 1 minus y squared, it's got an offset, and that offset is the constant term. So in fact, this is the original evidence that you've got antiquarks in there. You can see them in the scattering plots. Right? So it leads to the need for there being an antiquark term, and it leads then to the idea that what must be happening is that we have 3 valence quarks, and a q bar c, and therefore all quarks that we see are actually have a valence and a c component, whereas all the antiquarks are purely in the c. Where would that c come from? It would come, and we progress to this as we go along, from quark to quark gluon radiation, and then the gluons turning into q bar pairs. That's how you can generate it. Now, I wrote that very simply in terms of the results for neutrino and antineutrino, quark and antiquark. We've seen that. Now compare that to the general formulae that apply for neutrinos, and we will see that in this case for neutrinos it's still true that there's no longitudinal structure function. There's nothing for this piece to correspond to. But the F2 corresponds to a sum over Q and Q bar, and there's now a non-zero XF3 term which corresponds to a difference between Q and Q bar. So when we measure these structure functions for neutrinos, we'll be measuring the sum of quarks and antiquarks and the difference of quarks and antiquarks. Okay. I'm not going to dwell on this very much, but the truth is that if you think about it, neutrino scattering has to be flavor dependent. I've just been talking about generalized quarks and antiquarks. But think about it. If a neutrino is scattering, it's got to keep its lepton nature. So if a neutrino comes in, it's got to be a mu minus that goes out. It can't be a mu plus. You can't have lepton changing to anti-lepton at the vertex. So the exchange boson going this way must be a W plus. The W plus can only hit something like a D and become a U because you've got to conserve charge. You can't have a W plus hitting a U because that would make something with charge 5/3, which doesn't exist. So when you talk about quarks for neutrinos, only the down and the strange quark will be involved. When you talk about antiquarks, only the U bar and the C bar can be involved. And again, the opposite is the case if you think about the antineutrino scattering. So when we write these structure functions for protons in terms of quark plus antiquark and quark minus antiquark, it's actually different flavors we're talking about. Why was this not a problem? I've written that up again just there to recap what it was. The reason this was not a problem is because neutrino scattering experiments in the early days were never done off protons. Why not? Because the cross-section would just have been simply too small, right? They were done off big, heavy isoscalar targets like iron or neon at the lightest, right? What does it mean to be an isoscalar target? It means you have an equal amount of neutron and proton, right? So we need to know not just what do they look like off protons, but also what do they look like off neutrons. And to get from there to there, all you have to do is a swapping of your isospin, D for U. right? Because the idea is that the neutron with 2 Ds and a U and the proton with 2 Us and a D, a U in a proton looks pretty much like a D in a neutron and vice versa, right? That's the assumption that's being made here. So that's what it is off protons, that's what it is off neutrons. So for isoscalar targets, we add the whole lot together for both neutrino and antineutrino. And when we look at this, we say, well, actually that seems to show us that the structure functions for neutrino and antineutrino F2 are pretty much the same. And so are the XF3 structure functions, bar a little bit of mucking about with strange and charm quarks, which I'll come to later. The point is they're small, so it didn't make much difference. So, if I just continue with this construction and also write U's in terms of valence and C, and U bars just in terms of C, and the same for D, we will see that the XF3 there, if we look at it, it's really got to do with U plus D minus U bar minus D bar. Those are the dominant terms. If I write this in terms of valence and C, I'll see that U minus U bar plus D minus D bar just gives me all the valence quarks. So the XF3 structure function measures the valence quarks, whereas the F2 has everything added in, measures the valence and the C quarks. And I'm actually getting very close to the end now. I just want to sort of finish these quark-parton model results. Let's also compare F2 in neutrinos to that in electrons. We already wrote that on the proton it would be the quark charge squared times the relevant quark. So 2/3 squared for U's, minus 1/3 squared for D's, and so on. Whereas for the if you make that on an isoscalar target, P plus N over 2, you can do that yourself. You just write that again, swap U for D and add the 2 together. You'll get 5/18 U plus U bar D plus D bar, and a little bit of strange and charm. How does one relate to the other? This F2 for the charge lepton scattering is 5/18 times what the F2 is for the neutrino scattering, right? That's got U plus U bar D plus D bar in it as well. So does this. They're almost the same. Now let's look at the data. In fact, let's look at this piece of data first. This is a comparison of, in the black, F2 for neutrinos, in the open circles, F2 for charge lepton on deuterium, and we've already applied the factor of 5/18 in the plot, right? So I said on this page that there was 5/18 between them. This has already got it applied. So that is the, one of the triumphs of the quark-parton model is this really works, the 5/18 rule worked. But I might add, this didn't happen, this plot doesn't come from Feynman's day, it's about 20 years later, because I keep sort of sweeping under the carpet that there's a caveat about what's going on with the strange and the charm quarks. It took us 20 years to understand that and actually be able to apply it and see that it works, but it works, okay? And just before the end of the lecture, the shape of these distributions, I said we could measure with XF3 the shape of the valence, there it is. The shape of the F2 is the valence plus the C, so we can subtract one from the other and get the shape of the C. And the last thing that's kind of remarkable is I said XF3 measures the valence momentum distribution. If I divide it by X, that'll give me the number distribution. So if I integrate this over all possible momenta, I should get the total number of valence quarks in the nucleon. And this measurement was done, and here are the results. Now, I'm not saying they're tremendously accurate, but it is around 3, when in principle, if you think about it, it could have been anything, right? And this number could have come out as any finite number. It does come out as 3. So these are the reasons why we believe in the quark-parton model. So it's time for a break now, and then I'm going to, after the break, generalize this into QCD. Right.
Questions, please.
Yes?
I'm sorry, p squared is small. Was
Yes.
it necessary to do that? Because the equation was so easy to solve.
It was necessary just so that you could identify the fractional momentum exactly with the measurable kinematic invariant, right? The equation's easy enough to solve, but if you keep the mass squared in it, it's not exactly equal to that kinematic invariant. So it's a matter that we're trying not just to do theory here, but to measure things as well. What was remarkable, I didn't comment on it, is that actually when we saw that Bjorken scaling plot that things really seem to work and not depend on q squared, that was happening at really quite low q squareds. Feynman always thought that it would have to be a fairly high q squared for his approximations to be valid, but it isn't. And that's still one of the more remarkable things one can think of. Anyway.
Feynman and Bjorken, you might also tell us who GLS is in the previous slide.
Yes, well, that was the...
There it is. The GLS.
GLS, Gross, David Gross, Nobel Prize winner for QCD, and LS is Llewellyn Smith, who was a professor at Oxford for many years and was the Director General of CERN, and now he was involved with Sesame in this part of the world, right?
Useful.
So, you know. And it's not a matter of just saying, whoops, I think it should be 3. There's a lot of complex current algebra involved in actually proving that it's 3. So, you know.
What is this curve downstairs?
Actually, I mean, I'm trying not to mention some of the details, but actually the real answer to the GLS sum rule is 3 minus some quantities depending on alpha s and some non-perturbative terms. So those are the non-perturbative corrections there. So I'm just going here for the idea that the ballpark was 3. Yeah, there are modifications to that, yes. So.